Okay, section 6.3, generalized permutations and combinations. Example 1, how many strings can be formed using the following letters? Mississippi. Here we have 11 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 characters. So this problem can be considered a problem of filling 11 blanks like this with the given letters, 11 letters. So assign positions for the two p's are just choose 2 out of 11s. That ways that we have. So we have there are this many of ways to fill up 2 positions with p's. Okay, and once those 2 positions was filled with p's, then we have 9 positions left, and we have 4 s's here. So we have 4 s's to filled in 9 empty spots. So there are 9 choose 4 ways to fill S in addition to P. Then we have 5 positions left, and we have 4 I's. 4 I's. 1, 2, 3, 4. So we have 5 positions to be filled with 4 I's. So we have 5 choose 4 ways to fill 4 I's in 5 empty spots. Then we only have one position left to be filled with the letter M. That is one case. So by the multiplication law, the product rule, then we can multiply each disjoint ways by the multiplication principle. So 11 choose 2 times 9 choose 4 times C, 5 choose 4 times 1 choose 1, which is this, which can be found as 4,650 ways to make strings with these letters. Okay, and this also can be easily we have 1 M's and 4 I's and 4 S's and 2 P's. Then add all of them, which is 11. So 11 factorial over 4 factorial times 4 factorial times 2 factorial times 1 factorial. This is actually what we did. So if you multiply all these, then you will see this. 2 plus 4 times 2 plus 4 plus 4 plus 1, which is 11 factorial, over 2 factorial, 4 factorial, 4 factorial, and 1 factorial as a numerator. Then you have this. Okay. And theorem 2. Suppose that a sequence S of n items has this n1 identical object of type 1 and n2 identical object of type 2 and nt identical object of type t, then the number of ordering of S, the sequence S, is this. Addition of all this, which is n, over n1 factorial, n2 factorial, n factorial. So the earlier example is the one exercise problem of this theorem. And this theorem comes from those earlier observations. And proof is simple. Yeah. Like here, on first we choose n1 from n, then we have n choose n minus 1 ways of choosing type 1 items, and n minus n1 choose n2 ways for choosing n2 items of type 2, and so on. So product multiplication principle adopted here. Then we multiply all this. Then these things cancels each other, and one's left are n factorial over n1 factorial and n2 factorial and nt factorials are only left. This is the proof. Okay. Next. Yeah, the similar problem. We have this, then we have 8 characters, so 8 factorial. We have 4 b's and 2 two S's and two M's and 1 factorial of, there's no M. Here we have 4 B's and 2 M's and 2 S's. So this is what we have. So this is just consequence of the earlier theorem. Next, consider 3 books: a computer science book, and physics book, and a history book. We have 3 category of books. We have 3 books. Suppose that the library has at least 6 copies. Should have 6 copies. We should have of each of these books. We want to have at least 6 copies of these books. Okay. In how many ways can we select 6 books? There are 3 categories of books. Among these, we want to choose 6 books. Okay. What's the idea? Okay. Here is the here the idea is this. Important thing is we can have all 6 computer science books and no other books. That's the one way. We can have 3 computer science books and 3 physics books and no history book. Still, we have at least 6 books choice. So important thing is we can have an option of no books in 1 category or 2 category. Okay, and also the repetition is allowed. Repetition is allowed. Okay, we can have 6 books of same kind category. Okay, so this problem can be considered. We have 6 axes and 2 bars. So we have 8 objects. The idea is finding a position of this bar is located in between 6 axes. Okay, this is the idea. We can have a computer science book, physics book, and history book. We have 6 objects. There are 2 bars. We choose 2 bars where we want. Okay. So if we translated this problem to choosing the position for these 2 bars in between these 6 axes, then we have 8 options. We have 8 positions, and these 2 bars are located. So our choice can be 8 choose 2 ways of choosing those 6 books of 3 categories. That's the idea. Instead of just trying to just 6, we just list out 6 axes and find the position for 2 bars. So we have 8 positions to be filled with 2 bars. So 8 choose 2 is our choice, which gives us 28 ways of choosing 3 categories of books of 6, at least 6. Next, theorem 5. If X is a set containing T element, the number of unordered K element selection from X, repetitions allowed, is this. Why? This is the way. 이거는 T개 중에서 K개를 순서 없이 고르는 방법이 몇 가지냐는 걸 물어보는 거예요. Okay. So we have so this problem is repetition is allowed. So how many we have? This number is, and this left hand side is same as right hand side, because left hand side can be simplified with the right hand side like this. I think this is yeah, this is well known equation for choosing it, and this theorem shows this can be also written in this way, because we are choosing k out of t object without order. In that case, k plus t minus 1, choose k is the option for the answers. Next problem is the use of this earlier theorem. Choose suppose that there are files of red, blue, and green balls. So we have 3 types of balls, and that each file contains at least 8 balls here. So we are choosing 3 different types of object and choose 8 out of those 3 categories. K개 중에 아니라 K개의 이거 뭐지? K개의 이 뭐지? 주머니에서 이런 거죠. 주머니에서 T개의 주머니에서 K개를 순서 없이 고르는 방법. 이렇게 이해해야지 더 맞는 말이에요. Okay. So, with this theorem in mind, we have 3 바구니, and we are choosing 8 objects without the order. So, what we supposed to is choose k plus t minus 1, which is 8 plus t is 3, a is equal to k. So 8 plus 3 minus 1, choose 3 minus 1, t minus 1 is what we are looking for, which is 10 choose 2, which is 45. This is what we are looking for. And second problem is in how many ways we can select 8 balls. In how many ways can select 8 balls if we must have at least 1 balls of each color? Then all you have to do is choose 1 from each, and 3 is already taken, and we only need to choose 5 with the same conditions. So in this case, yes, 1 each ball of red, blue, and green balls were chosen, so it was fixed. It's one choice, and then we have 3 buckets to choose 5. So k is 5 and t is 3. So k plus t minus 1, choose t minus 1, which is 7 choose 2, which gives us 21. Okay, that's the same as choose 1 from each bucket first, and then 이거를 고르는 방법이 아니라 담는 방법이라고 하는 게 맞구나. 주머니에 T개 주머니에 K개를 순서 없이 담는 방법. 이 말이 더 맞는 말이죠. 주머니에 순서 없이 담는 방법. 오케이. 복사. 하나씩 미리 넣고, 이거 미리 넣고 3개 중에서 3개 주머니에 5개를 순서 없이 담는 방법. 오케이? 이렇게 무슨 말인지 이해되죠? 바켓이 있고 바켓에 저 공을 몇 개씩 다른 색깔 공을 몇 개씩 집어넣느냐 하는 그런 문제로 이해하면 바로 쉽게 이해할 수 있습니다. 오케이. 넥스트. 4개 바켓에 이거를 1개를 4개 상자에 2를 4개 상자에 이게 이 방법으로 이해하는 게 훨씬 더 맞는 방법이에요. 오케이. Next example. In how many ways can 12 identical mathematics books be distributed among the students? Anna, Beth, Candy, and Dan. Same problem. It's just we have t is equal to 4 and we have 12. K is equal to 12. So k plus t minus 1, which is 15, and t minus 1, which is 3. So choose 15, choose 3 is the answer. 455. Okay. Next. How many solutions in non-negative integers are there to the equation x1 plus x2 plus x3 plus x4 is equal to 29? How? How can we consider this? Okay, so this problem can be considered the object of 1, so natural number 1. We put the natural number 1 into 4 different boxes and add make it 29 times. Okay, that's how many ways that we can do such a job. Okay, so each solution of this equation is equivalent to selecting 29 items xi of type I, which I is equal to 1, 2, 3, 4. Then according to the theorem 3.5, then the number of selection is same as choosing k plus t minus 1, choose t minus 1. Here, k is equal to 29, t is equal to 4. So 32, choose 3 is what we are looking for. Okay. Okay. This is same as this. K is equal to 29 and t is equal to 4. Next problem is how many solutions in integers are there to the equation that satisfy this. Here, similar, but it has a condition like this. How? This problem, B, is selecting 29 items of xi's of type i's, and first select one item of type 1 first, because it should have at least one. Second, select 2 items of type 2 first, because we should have at least 2 of x2. And then third, we select 3 items of type 3. So we already choose 6 items. So how many items left? We have 23 items left. Then the problem is k is equal to 23 and t is equal to 4. So we choose 20 of 3, which is 2,600. This is the counting number. This is a way to do it. Okay, and here, so you have learned the permutation and combinations in high school years. Then now you have learned the way of counting with repetition allowed it. Okay, for the permutation you have this. For the combination you have this. Okay, when the repetition allowed it. And these are the exercise problems that you're supposed to solve, and I have uploaded all the solutions for you. Okay, then section 6.4 is the algorithm for generating permutations and combinations, and next 6.7 is a binomial equation and combinatorial identities. Yeah, we'll continue. Here, you have learned the cube of a plus b, which is this. Have you seen this? You have learned the square of a plus b. Okay, and you compute this. You will see how many of these terms are there. Anyway, here, a plus b cube is this. This number can be counted as this. Can be written in this way with the combination notation. 3 choose 0, which is 1. 3 choose 1, which is 3. 3 choose 2, which is 3. And 3 choose 3, which is 1. So this can be written in this way. So this binomial equation is related with the combinations like this. Okay. In general, n square of a plus b can be written as this. Okay. Coefficients are n choose k's on each terms. So like a plus b n to the nth power can be written as n choose 0 times a to the nth power times b to the 0th power. And it's n minus 1, then here n choose 1, n choose 2, then n minus 2, n choose n choose n minus 1, here 1 and n minus 1, n choose n, which is 1, then a to the 0th power n. So this is the generalization of this binomial equation. This is called the binomial theorem that you already know. And expand this using binomial theorems. What to do? With this theorem, all you have to do is to find the coefficients like this and powers like that. Then you can easily, you can write this one in this form. Then all you have to do is just to do the computation of combinations and powers to simplify in this way. That's what you have. Okay? Next. These are what you already have learned. Find the coefficient of this in the expansion of this. What's the coefficient of this? So this is what? It's here. And 5 plus 4 is 9. So n is equal to 9. And here, k is equal to 4. As you see here, the power of b. This is 4. So n choose 4, and a to the n minus 4, and b to the 4. This is what we are looking for, isn't it? So all you have to do is n is equal to 9 and k is equal to 4, because 5 plus 4 is 9. So 9 choose 4 times a to the 5th times b to the 4th. This is what we are looking for. Here 126 is the coefficient of these numbers. And the next, find the coefficient of this. Okay. This is called the multinomial polynomials. When we have x and y 2, then it's a binomial. When we have more than 2, 3, 4, and 5 terms of x, y, g, or w, or whatever, then we call it the multinomial polynomials. In this case, we have 3 variables x, y, and g. All you have to do is this. Only difference is we have 2 plus 3 plus 4 is 9. Okay. Then 9 choose 2 first. Then 7s are left. 7 choose 2 is 7 chooses is 3. Not 7 choose 3, isn't it? 7 chooses 3. 7 choose 3, and then we have only 4 left. So 4 choose 4. That's it, isn't it? This is the answer, which is 1,260. Isn't this simple? You can do the same thing for the multinomial polynomial with the 4 variables, x, y, g, w. Still, you can find the coefficient without difficulties, isn't it? All you have to do is just add all those powers and do the one at a time and multiply. This is a Pascal's triangle. And Nabil, you must have seen this. Okay, here you see 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. These are exactly matches with the coefficient of the binomial polynomials, isn't it? And also important thing is when you add 1 plus 1, it gives 2. 1 plus 2 gives 3. 3 plus 3 gives 6. 1 plus 3 gives 4, like this, isn't it? So addition of these two gives the bottom one, like this. This is an interesting fact that we can see from this triangle. From here, we can reduce this equality. This is n choose k, and this is n choose k plus 1. And this gives us n plus 1 choose k plus 1. This is what we have. Like this. From this picture, we can think of this. And we can prove this, like this. You just simplify this, you will have this. But there's a better proof. This is a better proof. Actually, this is a better proof. Who can explain this? Okay. So in this combinatorial argument of the proof, the way is the number of ways of choosing k out of n plus 1 can be found as adding the number of these two cases. First, one object, you choose one object first. Then you choose another k minus 1 object from other n object. Okay, that's the n choose k minus 1 cases. Done. Then the other case is the number of ways that object is not included in the selection. So you exclude that object, then you have n object left. Then you choose k object from that n object. That number is n choose k. Addition of these two cases covers all the cases that you choose k from n plus 1 object. Okay. That's the proof. So this can be written in this way as well. I just changing. Next, using the binomial theorem to derive the equation. This is 1 plus 1 to the nth power, which is 2 to the nth power, is exactly same as this, addition of this, because all the powers are ones. Isn't it? So this is a one corollary. And next, and also 1 plus x to the nth power can be written in this way. Okay. And there are many inequalities that we can find from those binomial equations. And also, this can be written as this, because of addition of this can be excluded and deleted from here. From this can be written as this. So we know C of ik is equal, I choose k is the same as this minus this. So this can be written in this way. This, or each term can be replaced in this way. Then what? I choose I is 1. So k choose k is 1. So this every middle terms are deleted. Then what's left is this, which is this. Okay, this is just computations. And find the sum of this from 1 to n. Then addition of these two is this, which is n times n plus 1 over 2. So this is the way, another way to find the rules. There are 3 exercises to be covered. And next, Pigeonhole principles. Okay, you have learned the Pigeonhole principles. This principle is called the Dirichlet's drawers principle or the shoebox principles. Idea is if you have 6, 1, 2, 3, 4, 5. If you have 6 pigeons and there are only 4 boxes, then, and if you don't see any pigeons in the air, then all 6 pigeons should be in some of the boxes. Here we can tell one of those 4 boxes should have more than 1 pigeons in it, clearly, isn't it? If you assign 1 pigeons in each boxes, then you still 2 pigeons left. So that should go into a box which is already taken by other pigeon. Okay, that's the idea. So if n pigeons fly into k pigeonholes and k is less than n, then some pigeonhole contains at least 2 pigeons. That is called the first form of pigeonhole principle. Okay, this principle can be applied to the names. The persons has first names Alice, Bernard, and Charles, and the last name Lee, McDuffie, and Angie. Then show that at least 2 persons have the same first and last names. How? There are 9 possible names for 10 persons. There are 3 first name and 3 last name. Then product rule adopted to have 9 different names. But we have 10 peoples, isn't it? 10 persons. There are only 9 possibility. So one's left. So somebody should have same first names in it. Okay, 9. pigeon and so you can match the person to pigeons and names to pigeonholes. Then the assignment of the name to peoples, then assigning the pigeonhole to the pigeons. So by pigeonhole principle, some name pigeonhole is assigned to at least 2 persons. Show that at least 2 persons have a same first 10 person. 여기서 10사람이라는 말이 빠졌네. 그쵸? There are 10 persons. There are 10 persons. There are 10 persons and the person has first names and last names. So that at least 2 persons have the same first and last name. Okay. 여기, 그러니까 이게 네, 무슨 말인지 알죠? Okay, next. Pigeon, second form of pigeonhole principle. If f is a function from a finite state x to a finite state y, and cardinality of x is bigger than cardinality of y, then f of x, if f of x1 is equal to f, then f of x1 is equal to f of x2 for some x1 and x2 which is not same. Okay. This is also a pigeonhole principle. 그러니까 무슨 말이냐면 x란 도메인이 있고 이제 y란 이제 코도메인이 있으면 그러면 이제 x가 더 y보다 많다면 이게 함수라 그러면 이게 배정될 거 아니에요. 근데 이 개수가 더 많으니까 하나씩 배정하다가 어떤 거는 다 채우고 나서 나머지를 채울 수밖에 없죠. 그러니까 당연히 겹치게 되는 f of x1과 f of x2가 같이게 되는 게 나올 수밖에 없죠. So this is just another form of pigeonhole principle. If you assign the x1 to y1, then x2 to y2, and x3 to y3, then after some point, because you have extra xi's over the number of yi's, so sum of yi's should be same. Okay? Next, show if we select 151 distinct computer science course numbered between 1 and 300 inclusive, and at least 2 are consecutively numbered. Same problems, easy problems. Third form. Let f be a function from a finite set x into a finite set y. Okay? F a function. Then suppose cardinality of x is equal to n and cardinality of y is equal to m. Then let k k be a ceiling function of n over m. Then there are at least k values, ai's, in kx such that f of a1 is equal to f of a2, f of ak. 이건 무슨 말일까? f가 x로부터 y로 가는 함수인데 k를 이렇게 정의하면 그러면 이게 하나씩 배정되는데 이게 실링 펑션이니까 어느 숫자까지는 멈춰 있게 되잖아요. 그러니까 몇 개는 쭉 같이 가다가 어느 선을 넘었으면 한 점프하게 되지. 그러면 그 인풋이 몇 개가 달라져도 쭉 같이 가다가 또 점프해서 올라가고. 무슨 말인지 알죠? 그러니까 for some of ai's it should be same. 실링 펑션이 이제 그런 의미가 있는 거죠. Next, example 8.5. Yeah. Yeah, this is also one simple examples, and I think that's the end of chapter 6. Okay, chapter 6. Yeah, one team will be prepared for solving these problems, and all other students should make a contribution of the problems and solutions that I already assigned, and I gave you solutions. And review problems are there. And there are writing projects that some of you may interest. And this is a summary. In chapter 6, we have learned the counting method and to find how many objects and ways and steps are there for these to estimate many things. And we have learned tools for counting, including multiplication principle and addition principle and permutations and combinations. And another basic principle include inclusion and exclusion principles. And we learned, in fact, permutation and combinations, and R permutations of n distinct objects, and are combinations of n distinct objects, and also with repetitions, and generalized permutation combinations with identical objects and unordered conditions. And we have learned 3 types of Pigeonhole principles. I think that's the whole chapter 6. Any questions?